Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss the vector space of linear maps. So in this topic, we will define scalar multiplication and addition of linear maps. We will consider the consequences of these definitions for matrices, which represent the linear maps from finite dimensional vector spaces to finite dimensional vector spaces. We will prove that the vector space of all such linear maps is indeed a vector space by going through all 10 axioms. And again, what's important to remember is that the vectors in this vector space are the linear maps themselves. That is, for example, we will have the vector space of all m by n matrices. We will also consider the definition of a norm for a linear map. Now, in order to claim that a collection of linear maps forms a vector space, we need a definition of a scalar multiple of a linear map and the sum of two linear maps. We will see also how these definitions apply to matrices. We will then prove that using these definitions, the collection of all linear maps A that map a vector space U onto a specific vector space V forms a vector space. Important. Each pair of vector spaces U and V defines a different vector space of linear maps. So we are going to see that, for example, if U is R to the 4 and V is R to the 7, then the vector space of linear maps from R4 to R7 are all 7 by 4 dimensional real matrices. And that will be a different collection from, say, all linear maps from R3 to R9. So, given two vector spaces U and V, if we have a map from U onto V and a scalar alpha, we will define the linear map alpha times A, which maps U onto V, by alpha times A applied to U is alpha times the result of A applied to U. That is, the map alpha A applied to U has the same effect of applying A to the vector U and then multiplying that result by alpha. Now, if A maps f to the n to f to the m and alpha is in the field F, what is alpha times A? Well, recall that every single linear operator from a finite dimensional vector space onto another one is representable by a matrix, specifically an m by n matrix where we have n column vectors of dimension m, in which case now A applied to U is a linear combination of the columns of A with each column multiplied by the corresponding entry in the vector U. Thus, we have that if A is this matrix of n column vectors, then alpha times A applied to U is just alpha times A applied to U, which is just alpha times this linear combination of the column vectors of A. But now we have a scalar times a number of vectors, so by the properties of matrix vector multiplication, scalar multiplication distributes over vector addition, we have that is equal to this expression here. However, each of those terms is two scalars multiplying a vector. And so therefore, by the properties of vector addition, scalar multiplication, we can rearrange the scalars. So now we have a linear combination of alpha times each of the columns of the matrix A multiplied by the corresponding entries of U. But this is just the matrix with column vectors equal to alpha times the corresponding column vectors of the matrix A, all multiplied by the vector U. Thus, alpha times A is every vector of A multiplied by alpha. Okay, here we have A mapping r to the 6 to r to the 4, and we have that negative 1.5 is a real number. So here's our matrix A. What is negative 1.5 times this 4 by 6 matrix? Well, we just multiply each entry by negative 1.5 to give us this matrix here. Thus, we can either multiply the matrix or a vector U by this new matrix, or we can multiply the vector U by the original matrix A and then multiply that resulting vector by negative 1.5, and you'll get the same answer. Similarly, given two linear maps A and B mapping a vector space U onto a vector space V, we will define the linear map A plus B, which also maps U onto V, where A plus B applied to U is A applied to U plus B applied to U. Now, that once again, the map A plus B is that linear map that has the same effect as first applying A and B separately to U, and then adding the resultant vectors in the vector space V. So suppose that A and B map f to the n to f to the m. What is A plus B? Well, recall once again that because this is a mapping from f to the n to f to the m, A and B are matrices that are m by n, and thus can be represented as matrices of n column vectors, each of dimension m. Also, A applied to U is the first linear combination there, B applied to U is that second linear combination. Thus, A plus B applied to U is just A applied to U plus B applied to U, which is the sum of those two linear combinations. But this is just a sum of vectors, so we can move the terms around by associativity and commutativity, and notice then that we can group them based on the scalars u1 through un. We can then factor out those scalars and note what we have. We have u1 times the sum of two m-dimensional vectors, plus u2 times the sum of two m-dimensional vectors, all the way up to un times the sum of two m-dimensional vectors. Well, this is by definition the matrix, the columns of which are the sums of the corresponding columns of matrices A and B, all multiplied by the vector U. Thus, A plus B sums the corresponding column vectors of A and B, which essentially means it sums all of the corresponding entries of the matrices A and B. So, for example, here we have two matrices A and B that map R4 onto R3, thus both are 3 by 4 matrices. What is A plus B? Well, A plus B is just the sum of the corresponding entries. So, if we wanted to apply A plus B to a vector U, we have two choices. We can either multiply U by the matrix at the bottom, or we can multiply U by each of the matrices at the top and add the two corresponding vectors together, and you will always get the same result. Now, you may be wondering, Why did we just not define what scalar multiplication of a vector is and what matrix addition is? Couldn't we have just done that and done away with the definition of scalar multiplication of a general linear map and the sum of two linear maps? Well, first, not all linear maps are matrices. So we had the more general definition. In fact, in your second year course on quantum mechanics, you're going to see a number of linear operators that are definitely not matrices. Second, notice what we did. We did not define alpha times a matrix and the sum of two matrices. Instead, we defined the general form of alpha times a linear map and the sum of two linear maps. We then saw what happens if that's what we do with matrices. So we derived the scalar multiplication of a scalar and a matrix and the sum of two matrices based on the definitions from linear maps. This is very important because in the next topic we're going to define composition of linear maps, and this is actually going to define matrix-matrix multiplication. Now, your first thought for matrix-matrix multiplication might be to take two m by n matrices and multiply the entries that are corresponding to each other. So basically, like adding two matrices, multiplying two matrices just multiplies the corresponding entries. Hint, we will not be multiplying two m by n matrices element-wise. You could define matrix multiplication in this way, but there's nothing beneficial from such a definition. Now, if A mapping a vector space U onto a vector space V is linear, we want to show that alpha times A is a linear map. Proof. Well, let us apply alpha A onto this linear combination of vectors in U. Well, that's just alpha times A applied to that same linear combination. And because A is linear, A distributes throughout that linear combination. That's the definition of a map being linear. Now we have a scalar times a sum of two vectors in V, and scalar multiplication distributes across vector addition. But now we just have two scalars multiplying vectors in V, and thus we can swap those values. So now we have B times alpha times A applied to U1 plus gamma times alpha times A applied to U2. All right, but wait a second. Alpha times A applied to U1 is the definition of alpha A applied to U1, and the same for the second. So now we see that yes, indeed, alpha A does distribute across a linear combination of vectors in U. Next, if A is a linear map from U onto V, then 1 times A is equal to A. Proof. Well, 1 times A applied to the vector U is just 1 times A applied to U. But A applied to U is a vector in V, and V is a vector space. and therefore 1 times a vector in V is just that vector, so this equals A times U. And this is true for all U, thus 1 times A is equal to A. Next theorem. If alpha is a linear map mapping a vector space U onto a vector space V, then a product of scalars multiplied by A is equal to alpha times the operator that results from beta times A. Proof. Well, alpha beta is a scalar, so a scalar times a matrix applied to U is just that scalar times A applied to U. But wait a second, at this point, A applied to U is a vector in V. So we have a product of two scalars times a vector in V. Well, therefore, we can rewrite it as follows. After all, A applied to U is a vector, and therefore all the rules of a vector space hold. All right, but wait a second. Beta times A applied to U is equal to, by definition, beta times A all applied to U. Oh, and wait a second. Now we have alpha times a linear operator times a scalar applied to U. Well, that's just equal to alpha times beta times A all applied to U. And this is true for all U, and thus the two algebraic expressions in the linear operator A are equal. Now, if A and B are both linear maps mapping a vector space U onto a vector space V, then A plus B is a linear map. All right, let's apply A plus B to a linear combination of vectors in U. Well, by definition, this is simply A applied to that linear combination plus B applied to that linear combination. Now, A and B are both linear, and therefore each of them distributes across the corresponding linear combination. Now we have a sum of 4 vectors in V. What we can do is group them based on the scalar multiple, and then because scalar multiplication distributes across vector addition, we can factor out the scalar. Oh, but wait a second. A applied to U1 plus B applied to U1 is by definition A plus B applied to U1. So we can now rewrite it as follows. And therefore we notice that A plus B applied to a linear combination of vectors is equal to A plus B applied to each of the vectors in the same corresponding linear combination. Next theorem, commutativity. If A and B map a vector space U onto V are both linear maps, then A plus B equals B plus A. Proof. Well, A plus B applied to an arbitrary vector U is by definition A times U plus B times U. However, both AU and BU are vectors in the vector space V, and therefore those two vectors commute. But that by definition is the linear operator B plus A applied to U. And thus A plus B equals B plus A for all applied to all U. Thus those two linear operators are equal, and thus linear maps under this definition of linear map addition is indeed commutative. Theorem. If A, B, and C map the same vector space U onto the same vector space V, if they are all linear maps, then associativity applies. Let's prove this. Well, let's apply this to a vector u? Well, by definition, we have one sum of two linear maps plus another linear map. So that just distributes across, by definition, of the sum of two linear maps. But now we're left with a plus b applied to u, and once again, we can write down that definition as a applied to u plus b applied to u. However, au, bu, and cu are all vectors in V, and vectors in V associate. Thus, we can write it as follows. However, we now notice that bu plus cu is just the sum b plus c applied to u, and now we have au plus a linear operator b plus c times u, and that factors out. Thus, a plus b all plus c is equal to a plus the sum b plus c. Thus, linear maps under addition are associative. Now, if a and b are linear maps, then for a scalar a, alpha times a plus b is equal to alpha a plus alpha b. That is, we want to show that scalar multiplication distributes over linear maps. Proof. Well, alpha times a plus b applied to a vector u is just alpha times a plus b applied to u. A plus b applied to u is just a applied to u plus b applied to u all times alpha. But now au and bu are simply vectors in V, and scalar multiplication distributes over vector addition in V. So we're left with that. However, the first is equal to alpha times a applied to u, and the second is alpha times b applied to u. And consequently, as we have the sum of two different linear maps applied to the same vector, that's just equal to the sum of those two maps, by definition, applied to u. Thus, alpha times a plus b is equal to alpha a plus alpha b when applied to each vector u in the vector space U, and thus these two linear maps are equal. If A mapping a vector space U onto a vector space V is a linear map, then alpha plus beta all times A is equal to alpha A plus beta A. So let's apply the left-hand side to a vector U. Well, alpha plus beta is simply a scalar, so that comes out. However, now A times U is a vector in V, and a vector in V distributes, the scalar multiplication distributes over the field addition. Now, looking at the first one, we see the first one is just alpha A applied to U, and the second is beta A applied to U. And so now we have the sum of two operators applied to U, which is simply alpha A plus beta A all applied to U. This is true for all U, and therefore the two linear expressions in linear operators are equal. Theorem. The zero map, mapping the vector space U onto the vector space V, where 0 applied to U is equal to the 0 vector in the vector space V, that satisfies A plus 0 is equal to A for all linear maps that map U onto V. Proof. 0 plus A applied to U is simply equal to 0 applied to U plus A applied to U. But 0 applied to U is the 0 vector in V, and the 0 vector in V plus another vector in V is simply equal to that other vector. Therefore, 0 plus A applied to U is equal to A for all applied to U for all U, and thus 0 plus A is equal to A. Finally, for any linear map A mapping a vector space U onto a vector space V, we will define the additive inverse of A as that map which takes U onto the additive inverse of A applied to U. So in this case, A plus its additive inverse is equal to the zero map. Proof. A plus the negation of A applied to U is, well, let's just distribute across. And now we notice that the second term is by definition the negation of A times U. So A applied to U plus its negation is equal to the zero vector in V. Thus, A plus its negation applied to U is equal to the zero vector in V for all U, and therefore A plus its negation must be equal to the zero map. Thus, we have now shown that the collection of all linear maps mapping a vector space U onto a vector space V forms a vector space over the field F. The individual maps in this vector space are the actual vectors. So we can add two linear maps together, and we can multiply a linear map by a scalar. This vector space is sometimes written as a script L with both vector spaces, the domain and the codomain, in parentheses. For example, script L of R4 and R3 is the vector space of all linear maps that map R4 to R3. That is, it's representable by the collection of all 3x4 real matrices. Now, recall, if A is a linear map from R4 onto R3, then the additive inverse of A is simply -1 times A. So if this is A, then its additive inverse is simply every entry in that matrix multiplied by -1. Also, the zero element can be found by multiplying any matrix in this space of linear maps by 0, and so we do see that 0 times the matrix A is indeed the 3x4 zero map. So, if the domain and codomain of a collection of linear maps are equal, then we have the vector space of all linear maps A mapping a vector space U to itself. This forms a special vector space that we will study more later. This vector space is written as script L with the common vector space that forms both the domain and the codomain. For example, script L of R to the 4 is the vector space of all linear maps that map R4 to itself. That is, it is a collection of all 4x4 real square matrices. Now, the second derivative, the derivative, and the identity operator are all linear operators on polynomials. Consequently, we may write that d squared by dt squared, d by dt, and the identity map are all elements of the collection of all linear maps mapping real polynomials in T onto real polynomials in T. You may recall again that bold-faced R with T in square brackets is the vector space of all polynomials with real coefficients of a real variable T. Now, these are all linear operators, and therefore a linear combination of these operators is also a linear operator. So now if we pick an arbitrary polynomial, here's a polynomial of degree 2, and we apply this linear combination of operators to P of t, well, that's just the operators applied to P of t with that same linear combination. Now, looking at this, the second derivative of P of t is just 10. The derivative of P of t is 10t plus 2, and that is all multiplied by 3, so that's 30t plus 6. And the identity operator multiplied by that polynomial leaves that polynomial unchanged. So 7 times that is 35t squared plus 14t minus 7. So we can add those up, and we get that the resulting polynomial is this polynomial here, 35t squared plus 44t plus 9. Now, can we define a norm on a matrix, or more generally on a linear operator or map? Well, how about the square root of the sum of the squares of the entries? Well, not very satisfying, because this cannot be generalized to, for example, the second derivative, which is itself a linear map. So this only applies to matrices. Unfortunately, this definition has no practical uses, at least in linear algebra, and consequently very few people use it. It's actually sometimes called the Frobenius norm. How about the following? Define the 2 norm of a linear map A as the maximum that map stretches the 2 norm of a vector in its domain. So basically what we do is we look at all non-zero vectors in the domain, and we calculate A applied to U and find its 2 norm in V. We divide that by the 2 norm of U, and that, interestingly enough, usually has a maximum value, certainly for finite dimensional vector spaces. So under this definition, if this norm does not go to infinity, the vector space script L of all linear maps mapping a vector space U onto a vector space V is a normed vector space. Now, one may think that you may be able to define an inner product on matrices or an inner product on linear maps, just like we did for finite dimensional vectors. One could, at least for matrices, just define the sum of the element-wise multiplications of the 2 matrices, but once again, as you may guess, this has no practical applications, and so while one could use this definition, no one does. Now, following this topic, you know that the collection of all linear maps from one vector space to another forms itself a vector space. You know the definition of scalar multiplication of linear maps and the addition of linear maps. You've reviewed proofs that this is a linear map by seeing that all 10 axioms are true for this definition of vector addition and scalar multiplication of linear maps. And again, you will recall that the vectors in this vector space are the linear maps themselves. You are also aware that there is a norm on linear maps, or at least a potential norm. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!